So our final group is Conal, Brady from Conal School, first-time participant. Aidan, Chun, Roosevelt High School, first-time participant. And Luke Jones, one of our most senior participants. This is Luke's 4th time in the program, although it feels like the 10th. Feels like the 40th. It's your 3rd time? See, it's your 3rd time in the program?
I went 2014 and then the 9 minutes.
Oh, okay. So it's your 3rd time in the program. But see, it feels like more than that. Okay. Great. And the mentor for this project is Tucker Jones. So Tucker is a postdoc here at IFA. And oh, great, Tucker. Hi. Thank you. Okay. All right. Thanks, guys. You ready?
Go. And you have to advance.
So hi, I'm Conal Brady. This is Luke Jones and Aidan Chun. So today we'll be talking about galaxies. So our title is Hubble versus Hubble. We'll explain that later. And past and present measurements of H0 and implications for the future of the local group.
Alrighty, so let's talk about our project goal. So when we say Hubble versus Hubble, what do we mean? So there are 2 Hubbles that are in our project. We have this fellow here, Edwin Hubble, and we have the Hubble Space Telescope. So you will be hearing the word Hubble a lot, and I'll eventually start rambling going Hubble, blah, 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 blah. But this, we're just going to call the HST, and then we'll either call him Hubble or Edwin. But before we go over what our project is, Aidan's going to talk to you about some core concepts.
So basically, wait, which one is? So basically, the type of concepts we're going to go over are Hubble's constant, escape velocity, and local universe. So to start off with Hubble's constant is a proportional constant that explains the rate of the expansion of space. So it's kind of like how fast and the acceleration of space expanding. Oh, and it's in kilometers per second, per megaparsec. So H0 is in kilometers per second per megaparsec. The next concept we're going to go over is escape velocity. And it's the minimum velocity to escape gravitational attraction, in this case the local group. And if you exceed the escape velocity, you would less likely go in orbit or get attracted by the attractor, or in this case the local group. So the equation is escape velocity equals the square root of 2 times Newton's gravitational constant times mass divided by r, which in this case is distance between the 2 objects. The final thing is local universe. And all the local universe is that it's just a range of 20 megaparsecs around our galaxy. The HST Key Project is a project to recalculate the Hubble constant. Scientists use data from the Hubble Space Telescope to remeasure distances because Edwin Hubble measured distances on a very wrong, he was very incorrect. Likewise to Joseph, Sans, and Emma's group, we're kind of doing almost the same thing in that equation over there, which determines the velocity depending on the Doppler effect. So we get the rate of velocity equals c, or the constant speed of light, times wavelength obs, or the apparent wavelength, and wavelength rest, which is the actual wavelength minus 1.
Alright, now we're talking about the Hubble constant because that is the core of our project. The problem with galaxies is that they're really big and they're really far away. So our project was, worked on a lot of both theoretical and astrodynamical perspectives. So the Hubble constant is H0, it's this little thing right here. So Edwin Hubble originally theorized the Hubble constant H0 as a rate of expansion of the universe. And at the time, Albert Einstein was developing his, what is now the cosmological constant of the universe. But at the time, was supposed to be something that he was going to tie into general relativity for how the universe was static. But Edwin Hubble took these measurements right here, which we now know are very, very wrong, but we'll get to that later. And he saw that the farther away galaxies are, they are moving away from us at a higher velocity. So he was able to conclude that space is actually expanding, and h0 is the rate of expansion of space. So here are some numbers throughout time for h0. So his original calculation was 500 kilometers per second per megaparsec, which is really wrong. That's due to instrumentation errors at the time, because astronomy has come light years, no pun intended, from where it has been in the past. So the HST Key Project recalculated the Hubble constant, and the more or less, there's different values, especially because h0 isn't technically constant. It moves, but we're going to pretend that it doesn't. It's been calculated to be 72 plus or minus 8 kilometers per second per megaparsec. And that is from this paper here. And then we actually went and using data from the HST Key Project, which was given to us by our wonderful mentor, we calculated the value of 73.66 kilometers per second per megaparsec. And that's the last time I'm going to say those units. So our calculation does fall within that range. And what we did is we took all of the data from, no, I shouldn't say all the data because there's a ton. We took data from the HST Key Project, and we took Edwin Hubble's data, and we derived that data into a bunch of different graphs. So now Con is going to talk to you about data analysis. There's a lot of graphs, so make sure you brace. Oh yeah, that's right, I'm doing the first three. Never mind. Okay, so this is the same graph that you just saw. So the horizontal axis here is distance in 10 to the 6 parsecs. That's basically a megaparsec. No, wait. It is a megaparsec. And then the vertical, the other horizontal axis, is velocity in kilometers per second. So although all these numbers are wrong, and we actually took his data and we remade his exact graph. This trend line's a little different, but for all intents and purposes, it's the same thing, right? So it wasn't his analysis of the data that was wrong. It was the data itself, because instrumentation at the time was nowhere where it is now, and he thought things were way, way closer than they are. For example, a galaxy that we now know is 20 megaparsecs away, he thought it was 2. So you have a really big difference, and that's what changed his understanding of the value. But we took the actual HST values and we did his graph, but with better data. And you can see that you still have the same rate of the farther away a galaxy is, the faster it's moving away from us, the faster it's redshifting from us. So there's redshift and blue shift. Redshift means it's going away from you, blue shift means it's coming towards you.
Okay, so the next thing we're going to talk about is using Hubble's data. We're going to look at the distance and escape velocity for these galaxies. So, as you see, we get a really nice curve here, which you don't see often, so it's really nice. So we have galaxies start up here, and they come down here. So basically, what this is saying that the closer the galaxies are to us, the higher the escape velocity speed will need to be. When you come down, the distance gets greater, and as the distance gets greater, the less escape velocity speed you will need to exceed it. So as you can see, it comes down, and as you get farther away, the escape velocity speed gets smaller. Yeah. Okay, and as you can see, both Hubble's and HST's graphs are pretty much exactly the same, with the only notable difference being the distance and some of the escape velocities. I'd also like to say, I forgot to mention this in the other slide, but distance and the escape velocity are inversely related, so as I mentioned, if the speed is high, the distance is low. If the distance is high, the speed is low. Okay, so what you're looking at now is a combination between the velocities, which Luke presented, and the escape velocities, which I just presented. So you have the curve right here for the escape velocities, and the linear line right here showing the just regular velocities. Now, as you can see, the two lines intersect. At around that point, intersection is 0.8 megaparsecs, as that is the distance where the galaxies can exceed the escape velocity. So as you can see, you have galaxies down here which don't exceed the velocity, and galaxies up here that do. And over here we have the corrected data, which around 3 megaparsecs, and with the HST data, you can see that the escape velocity is exceeded. And I want to note that over here you can see that far less galaxies don't exceed the escape velocity, while in Hubble's you had a lot more galaxies that didn't exceed the escape velocity. Okay, so during the process we took 7 different galaxies and we compared them side by side. So the blue dots, there are 2 points for each galaxy. You have the blue dot, like as I mentioned, is the velocity, and the red dot, which is the escape velocity. So in Hubble's data, 3 to 7 galaxies did exceed escape velocity, and 4 to 7 didn't. And in the HST data, 4 to 7 galaxies exceeded the velocity, and 3 of them didn't. So all these down here, one of them, Andromeda, are coming closer towards us. Okay, now this graph shows the escape velocities using Hubble's data and HST's data side by side. So you can clearly notice that the escape velocity for Hubble's needs to be much higher. And that says that the distances would need to be much closer, like I mentioned. The higher the escape velocity, the closer it would need to be. So this says we have a greater expansion of the universe using HST's data compared to Hubble's data.
All right, so those were a lot of graphs. I'm going to kind of try and wrap it all up for you. So the value of H naught was estimated, and our estimation is consistent with the HST Key Project, which is really important for making sure that all of our charts and graphs are relevant. So we then calculated the escape velocities for both the HST and the original data. We did do some other calculations, but those were mostly conversions, like for example, turning distance in kilometers into distance in megaparsecs, stuff like that. We only showed one equation in this entire presentation. There was some more math, not a whole lot, but math is not fun to talk about. So that happened behind the scenes. It existed. You don't need to know about it, really. And we know that the HST data, as Con said, more of our sample galaxies will escape from the local universe. That's that 20 megaparsec range that we arbitrarily defined because it was convenient, when compared to the original data. So that means the exact numbers were, and you can't really do an apples-to-apples comparison because they weren't the same galaxies, but it was around 80% of our HST data, the galaxies would escape the local universe. And in the other one, you would have 40. Now, that doesn't really work because the galaxies, they weren't all the same. But with that, what were the 7 out of 10 number? Or sorry, what were the out of 7 numbers for the other ones?
It was like 3.7 for Hubble's and 4.7 for HST.
Yeah, so you still have that same basic correlation where under HST data, more galaxies are escaping the local universe. So that kind of wraps up our project. Acknowledgements, a huge thank you to our mentor, Tucker Jones, for putting up with us as well as helping us with our project. All the people who make HiStar happen, Dr. Jeff Matthews, Mr. Mike Nasser, Dr. J.D. Armstrong, the OG, and Mary Ann Karaoka for being the one who started this project, or started this program, because it's honestly been amazing, and we all thank you for getting this off the ground way back when. Final thanks to all of our HiStar peers, our brave and fearless leader, Michaela Wandel, and all of you for being here and listening to us talk. So yeah, thank you. So I don't think there are actually 3 minutes because we're probably over time, but any questions?
Yeah, just like a really brief question from anyone.
Well, I can be brief.
Jeff?
Okay, so you were calculating your escape velocities. You were calculating the escape velocity from the Milky Way galaxy.
It wasn't the Milky Way galaxy. It was, if you mentioned, it was a little bit confusing because we said local group and local universe. So the Milky Way is not the prevalent gravitational attractor. When we take the local group as a whole on the scales that we're looking, it's the local group as a whole that's the gravitational attractor. So that's why also in if we go way, way back really quickly, I promise, Mr. Nasser, I promise we'll get them out of here soon. As he sits here and looks really pleased. So when we took the mass of our gravitational attractor, it was actually way, way bigger than the Milky Way. I'm not actually sure how big it is. I probably should have put that down because now I forget. But it was the local group that was the attractor, not the Milky Way.
Okay, great. Thanks for correcting.
That's what's massive.